Welcome to this lesson on division and factoring for problem solving and data sufficiency problems on the GMAT. So let's first just define how division functionally works. So you can see a sample long division problem here whereby we are dividing 5 into 17. So the way by which we would process this is we'd say that 5 goes into 17 3 times, and we'd subtract out that 15 that 5 goes into 17 evenly, and then we'd have a 2 left over, which 5 cannot go into, and that would produce a result of 3 remainder 2, because 3 times 5 is 15, and 5 can't go into 2. Now, we need to name all of the pieces here. So the 3 is what is known as the quotient. It's the amount of times that 5 went into 17. Now, the 2, obviously, is the remainder. We've already kind of discussed that. Now, the 5 is what is known as the divisor or factor, and the 17 is the dividend, which is being divided into. So, there's a bunch of different ways that you can notate 17 divided by 5. Obviously, 1 is just 3 remainder of 2. But we can also notate it a couple of different ways. So first is as an improper fraction, and this is going to be the preferred method by which you're going to actually note 17 divided by 5 as a fraction, as opposed to the mixed number, which is 3 2/5. Mixed numbers are basically useless for calculation, so if you are working math on the GMAT involving fractions, you're going to want to do it all with improper fractions and only use the mixed number if you have to compare against answer choices as a final step that are in mixed number notation. And then the last way that we can articulate 17 divided by 5 is as a decimal, which is 3.4. So we then have to consider what this means for the remainder. And so there are several facts that we need to consider involving remainders. First is that there's a set range for a remainder. The remainder has to be greater than or equal to 0, but less than the divisor. Because if I'm dividing something by 5, I can never have a remainder of 6 or more, because if I have a remainder of 6, it's obviously going to go in 5 one more time, and I'd have an actual remainder of 1. But the remainder is going to be equal to 0 when your divisor goes into the dividend evenly. So if the remainder ever is set equal to the divisor, you're going to have to add 1 to the quotient, and your remainder basically resets as 0. So if instead of dividing 5 into 17, we divided 5 into 20 and said 5 goes in 3 times with a remainder of 5, that's not actually how we're going to articulate the math. We'd actually say that, of course, 20 divided by 5 is just 4, evenly with no remainder. So once the remainder is equal to the divisor, you add 1 to the quotient and you reset the remainder to 0. Furthermore, your remainder over your divisor is what is equal to your decimal left over as a fraction. So in this case, our remainder is 2, our divisor is 5, so we know that the quotient was 3. The remainder of 2 out of 5 is how we got our mixed number of 3 2/5. But our decimal is not 3.2, because 2 out of 5, when we set it with a denominator of 10, because all decimals are on powers of 10, that's going to be 4 out of 10 is equivalent to 2 out of 5, and therefore we'd have 3.4 as our decimal, because the decimal left over is, as a fraction, is equal to your remainder over the divisor. So now let's just consider some simple divisibility rules for integers that will be helpful, especially as you try to logically estimate to avoid unnecessary calculation. So the first integer we'll consider is actually a bit of a trick. It's dividing by 0, and nothing is divisible by 0, at least according to the GMAT, because 0 technically can go into any value an infinite number of times. So the result of dividing by 0 is infinity, which is a non-real number. And all arithmetic on the GMAT is assumed to be real. So therefore, you cannot divide by 0 when it comes to the GMAT. This concept will usually show itself on a data sufficiency, where if you divide by 0, you'll basically determine something is not sufficient. So Always remember that you cannot divide by 0, at least on the GMAT. Now, everything, however, is divisible by 1, because 1 will go into everything. It's just the way the arithmetic system works. Now, even numbers are going to be divisible by 2, and that's any integer where the units digit is even. So if you have an even units digit, the entire integer itself is even and divisible by 2. Now, a neat trick is you can determine when an integer is divisible by 3 by summing the digits to see if that sum is divisible by 3. So for instance, 96 can be proven as divisible by 3 itself because 9 plus 6 is 15, and 15 is divisible by 3. So this is a really handy way to, again, avoid excess calculation, because you can just add the digits and go, okay, if that sum is divisible by 3, the entire number itself is divisible by 3. Now, you know that a integer is divisible by 2 you know when an integer is divisible by 4 if 2 divides evenly into the integer an even number of times. So when you're doing these divisibility rules, very frequently you'll be creating what's known as an all-factor pairs chart, and you'll know how many times 2 went in, and if that number of times 2 went in is even, 4 is going to go in exactly half that number of times. Now, 5 is an easy one. Most people know if the units digit is either 5 or 0 for our integer, then the entire integer is divisible by 5. You know an integer is divisible by 6 if the integer is divisible by both 2 and 3. So that means if you've got an even where the sum of the digits is divisible by 3, the integer is divisible by 6, because those are the prime factors of 6, 2 and 3, that is. Now, for 7, it's a nuisance. There isn't a great shortcut for 7. There is one that we're not going to go into, because long division is really just bad marketing. As we saw with our example to start this lesson, you can do long division relatively quickly, and you'll just want to long divide 7 if it shows up as being relevant. And then, if you divide by 8, you'll know that an integer is divisible by 8 when 4 divides evenly into the integer that is the dividend, as it were, an even number of times. So, again, you'll probably be doing this in a list, and if 4 goes in an even number of times, you know 8 will go in exactly half of that, and you can have the number of times 4 went in. Then 9 has a similar rule to 3 in that the sum of the digits is divisible by 9. For instance, 189, because 1 plus 8 is 9, 9 plus 9 is 18, and 18 is divisible by 9, thereby 189 is divisible by 9. And lastly is 10, and again, you probably know this rule, where the units digit is 0 means that an integer is divisible by 10. So how does this play into the actual exam? Well, that's going to be if we've got to consider something like the factor pairs, and you'll be able to do this in a chart. So let's just think about the number 72. So the first factor pair of 72, of course, is 1 and 72, because 1 goes in to every number, and every number is divisible by itself. So your first factor pair is always going to be 1 and the number itself. Now, 72 is even, so 2 goes in exactly 36 times. We also know that 7 plus 2 is 9, so therefore 3 is going to go in exactly 24 times. Now, here's where we start to see the relationship between 2 and 4, because if we multiply 2 by 2, we get to 4. If we divide 36 by 2, we get to the number of times 4 goes in evenly into 72, which is 18 times. So everything involving the factor pairs is proportional. And again, this is just how arithmetic and multiplication and division work. And that's why we have had arithmetic for millennia, or at least a millennia. Now, 5 we can see will not go into 72 because it does not end in a 0 or a 5, but 6, because 3 goes in an even number of times, is going to go in exactly 12 times, because 6 is twice 3, and of course, we saw that both 2 and 3 work here. Now, 7 will not go into 72 because 7 goes into 70 10 times, remainder of 2, so that's not going to be a viable factor. But 4 goes in 18 times, which is an even number, so therefore 8 has to be a factor of 72, and it goes in exactly half as many times as 4, which is 9. And as soon as you get to the other side, you know you're done testing all of the factor pairs. So this is one way in which you may need to factor. So let's consider some facts about factorization. First, the greatest factor of any integer is going to be equal to the least multiple of that same integer, which is the number itself. And we can see that there, right? 72 is the greatest factor, and it's the least multiple because 72 times 1 is 72, which is the number itself. Now, A neat little trick that can help you decide if something is prime or if we've finished all of the factors is that once a possible factor squared is greater than the dividend, all factors have been identified. So what that means is we got to 8, right, in 72. And obviously we see with 9 that we've gotten to the other side, so we wouldn't really have to test it on this specific factorization chart. But we know that 9 squared is greater than 72. So each factor pair of 72 must include a value less than 9. So as soon as we got to 8, 8 squared, of course, is 64, which is less than 72. So 8 can be a smaller factor of 72. But once we get to 9 squared, we're done because 81 is greater than 72. Now, the least common multiple is another term you might hear. That just means the first multiple common to two integers. And the greatest common factor is going to be the largest factor common to two integers as well. So these are, again, some terms that they may use, and an all-factor pairs chart will be helpful to determine. Now, the other way in which you might encounter factoring on this exam is going to be as far as a prime factor tree goes. So we'll consider the same number, 72. And when dealing with a prime factor tree, you want to split it as evenly as possible as opposed to just dividing by 2, which I know is how most people will deal with prime factors, because it's going to shorten your tree. So we know that the most equitable factors of 72 from the pairs chart that we just looked at are 8 and 9. So we can split 72 into 8 times 9. Then we can split that 8 into 4 times 2. And we can split that 9 into 3 times 3. And because 2, 3, and 3 are each prime numbers, we can't split them any further. But there is, of course, the 4, which was a factor of 8, which we could split into 2 2's, and now we have all of the prime factors of 72. We've got 2, 2, 2, and 3, and 3. So if we multiply all of those 2's and all of those 3's together, we will get 72. So some facts about prime factorization. First, the definition of a prime number is that it's an integer that is greater than 0 with exactly 2 factors, 1 and itself. And we know that 2 and 3 are each prime because their only factors are 1 and the number itself. Every integer has a unique prime factorization. So that means here that 72 is the only integer that is comprised of exactly 3 2's multiplied by each other and 2 3's. So it has a unique prime factorization of 2 cubed times 3 squared. And any integer with 3 factors of 2 and 2 factors of 3 will thereby be divisible by 72. And if you add factors, you're just kind of increasing, and we still know that that integer with additional factors will be divisible by 72. And any integer with fewer than 3 factors of 2 and 2 factors of 3 will be a factor of 72. So, for instance, we know that 2 times 2 times 3, or 12, is a factor of 72 because 12 has prime factorization of 2 times 2 times 3, and there are 2 2's and 1 3 in 72, so therefore the integer itself that is comprised of exactly 2 2's and 1 3, 12, will divide evenly into 72. We also know that 1 is not prime, and 2 is the first and only even prime number, as we kind of already stated, because any other even is going to be divisible by 2, so only 2 is prime as far as evens go. And 1 is a unique case because 1 only has a single factor. It doesn't have 2. It's got just itself, so it is technically not prime. So, let's go take a look at a problem-solving and data sufficiency example involving some of these concepts around division and factoring. Okay, so let's consider a simple problem-solving question involving some of these concepts around remainders. So, as always, we're going to set up the scratch first. So we got A, B, C, D, E. We've got our answer choices as simple numbers, so we'll just write those out, potentially for process of elimination or back solving if we were to determine that those options were viable. So we find out that if we skip to the end of the problem, that we're being asked for a possible remainder. So we'll just write that as what we're seeking, a possible remainder. And We'll just have that over here. So now we'll start reading the question from the beginning, taking notes as we go. So we find that when integer x is divided by integer y, so we're taking x divided by y, that produces a value as a quotient of 36.45. So we want to figure out what a possible remainder when x divided by y might be. So first, we've got to remember that our remainder over the divisor is equal to that decimal leftover. As a fraction. So we've got to write that 0.45 as a fraction. And we know that that's 45 100ths, so we can do so as just 45 over 100. So now we've got to simplify this fraction in order to figure out what the remainder could possibly be. Because we know that when we get the fraction down to its least form, that we can only multiply up and keep integers, because we're told that x and y are each integers. So we can see immediately that 45 and 100 are both divisible by 5. So I can divide by 5 over 5 as a fraction to reduce this. So 45 divided by 5, of course, is going to be 9, and that means 100 divided by 5 will be 20. Whoops, not 25, 20. So that means that our least possible remainder is going to be that 9. And we could have an 18, we could have a 27. It can multiply up as long as we keep the fraction proportional and equivalent. So now we just go to our answer choices. And of course, 2 is not going to work because I can't reduce 9 down to 2 and keep integers. 9 can't reduce down to 3 and keep an integer as our denominator, which, remember, the denominator is going to be our divisor, so that's not going to work. 8, again, we can't reduce 9 down to 8 without getting the 20, our divisor, to no longer be an integer. 9, of course, matches 9, so we keep that. And 20 is a trap because that's our divisor, and our least possible divisor, to produce a value of 36.45 when we work with the actual integer x and integer y. So here is an example of how to work through a problem-solving question involving remainders, and this is frequently one of the more difficult concepts on the exam. So next, let's go ahead and take a look at a data sufficiency involving these concepts of remainders and factoring. Now, let's take a look at a sample data sufficiency involving these concepts of factors and multiples. So we start, of course, by writing out what we know. And in this case, we don't know a heck of a lot, and it really just starts with the question. So it's asking, is 25 a factor of a squared? And as always, we want to note that this is a yes-no data sufficiency, and we'll box that off. So, since we're talking about a squared, and we want to know, is 25 a factor of a squared, we really just have to break this down to what a requires as a factor. So, in order for 25 to be a factor of a squared, we're looking at 25 being equal to 5 squared. So we know that 25 is equal to 5 squared. And since we're looking at the factor of a squared, what we really need to know, if we just consider our need, is 5 a factor of a, right? Because if 5 is a factor of a, then we know that 5 squared is going to be a factor of a squared, and thereby 25 is going to be a factor of a squared. So condition 1 says that a is a multiple of 3. So if a is a multiple of 3, that really doesn't impact whether A is a multiple of 5 or 5 is a factor of A. Now remember that when you're dealing with yes-no data sufficiencies, it can be beneficial to consider circumstances by plugging in. So let's just say, well, if A is equal to 3, then the answer to the question about A squared having 25 as a factor is no, because A squared is equal to 9, and we know that the answer is no. But we've got no limitation saying that A doesn't have a factor of 5 paired with that multiple of 3. So if A were to equal, say, 15, 15 is a multiple of 3, but it's also a multiple of 5. And A squared here would be equal to 225. And of course, 25 is a factor of 225. 25 would go into 225 9 times, and we'd have a yes. And if this is the case, and we've got both a no answer and a yes answer to our question considering the condition, we know that our first condition is not sufficient, so our options remain B, C, or E. So then we consider condition 2. So condition 2 tells us A is not a multiple of 5. So 5 is not a factor of A. So if 5 is not a factor of A, then we know that technically A squared is not going to have 25 as part of it. But if we want to prove it out with a couple of examples, we can still do so. So we could keep condition 1, plug in of 3, right? Because that's going to work. We could still say A is equal to 3, and we know that A squared would therefore be 9, and we know that the answer to this would be no. But A can no longer equal 15, because if A is 15, then 5 is a factor of A, and we know that we can't have 5 be a factor of A as required by condition 2. So the answer here is always no. And always no is going to be sufficient, because we're not being asked, is the answer yes? We're being asked, is the answer consistent with a yes-no data sufficiency? And in this case, condition 2 is sufficient in telling us that no, 25 is not going to be a factor of A squared, and we'd select choice B. So go ahead and practice some of these concepts involving factorization and divisibility holistically on your own with some practice problems for the GMAT.